Hello everyone, in this video I'm going to discuss another multi-diode circuit, hopefully to guide you through the process of dealing with more than one diode in a circuit. As I explained, if you want to blindly approach the problem, you actually have to assume that each one of the diodes in a circuit could be on or off, and that could be quite cumbersome, especially if the number of the diodes increases. In this case, for example, you have to consider 6 different circuits before you can actually invalidate the wrong assumptions and find which one of the assumptions, which one of the operations is actually valid. But generally, there are ways to kind of reduce the number of cases that you consider by quickly invalidating some obvious assumptions. So I'm going to give you an example in this specific case. Now, for this specific circuit, this node right here is a very important node. The voltage of this node, I'm going to call that V1. The reason is that that node actually is connected to the anode of all 3 diodes, and therefore that voltage is going to define whether or not any of these diodes are on or off, because on the other end you pretty much know what happens to the voltage of the cathode, and therefore voltage of the anode is critical in terms of understanding whether the diodes are on or off. Now, for D1, the other end, the cathode end of the diode is connected to ground through a resistor. And what that means is that if V1 is anything above the turn-on voltage of the D1, then D1 is on. In other words, if V1 is greater than 0.7, that guarantees that D1 is on. Let's again repeat this condition. So for any diode, let me actually quickly do this. We have this, if we are using this rather simplified operation or IV curve, then as long as the diode is off, the current that is passing through the device is, so this is the current, this is the voltage of the diode, so VD, and this is the current of the diode. So we either have the voltage, the current being 0, or the voltage being a constant, and let's say we assume 0.7 volts. Now, therefore, right at the edge of this operation point where the diode switch is on, the current changes from 0 to something positive, and then the diode turns on. So since, let's assume that D1 is off and the voltage right here is something less than 0.7, and at that point the cathode voltage is actually ground, because there is no voltage, 0, because there is no current passing through R1. I'm going to call that I1. So I1 is 0, and therefore as long as the diode D1 is off, the cathode is connected to a voltage equal to 0, and the voltage V1 has to reach something above 0.7, which is basically the turn-on voltage of the D1, before you're going to start getting any current passing to R1. And again, therefore, any voltage above 0.7 volt is going to guarantee D1 to turn on. Now, the same thing you can say about D2, but this one, this time V1 has to be anything greater than -5 plus 0.7. So for the first one was 0 plus 0.7 for this one to turn on. For D2 would be -5 plus 0.7, which is -4.3 volts. And this is going to guarantee that D2 is on. And finally, for D3, V1 has to be anything greater than minus 10 plus 0.7, which is minus 9.3 volts. And therefore, that guarantees that D3 is going to be on. Now, one thing that you have to notice here, which is an interesting observation, is that in any of these situations, there are conclusions that you can make. For example, if V1 is anything greater than 0.7, then automatically V1 is also greater than minus 4.3 and V1 is greater than minus 9.3. In other words, when D1 is on, D2 and D3 are both also on. So you can't have a situation where D1 is on and any of the D2 and D3 are off. And that gives you a lot of information in terms of how to make assumptions about the operation of the two diodes. In other words, if you only have one diode in the circuit on, that could only be D3. That's a pretty good information to have. Now, this also tells you that in no situation all three diodes are going to be off. That's obviously impossible, because if that's the case, then the voltage V1 has to become 15 volts because there's no current passing through this resistor if all three of the diodes are off. But that immediately means that all three diodes actually are going to turn on, because then 15 is greater than 0.7 and therefore all three turn on. So the assumption all three diodes off is not going to stand ever. So at least D3 is on at all times. And then if D2 is on, D3 is definitely on. And if D1 is on, D2 and D3 are on. These are all the conditions that you can quickly conclude based on the circuit and what we have down here. So with that, now I can start writing conditions for any of these situations to happen one by one. And in order to do that, I'm going to actually put V1 right at the edge when this happens. Basically the diode is going to turn on, and write equations that relate these resistors to each other. So let's do that. So if we set V1 equal to 0.7, then we're right at the edge where V1 is going to turn on, assuming that I1 is equal to 0. So I1 equal to 0, but V1 is 0.7. And that means that D1 is about to turn on. And with that, we're going to write these equations. We have the KCL. I4 is equal to I2 plus I3, and I1 is 0. Then I4 is equal to 15 minus 0.7 divided by R4. I3 is equal to, this is 0.7, so the voltage down here, right here, becomes 0. So that would be 0 minus 10 divided by R3. And finally, I2 is equal to 0 minus 5 divided by R2. So this gives you the condition, relate the resistors for the condition where V1 is 0.7 and the diode D1 is about to turn on. And obviously I've already assumed D2 and D3 are on, because we said when V1 is 0.7, these two other ones are definitely on. And now we put V1 equal to minus 4.3, and this time obviously I1 is 0 from these conditions we mentioned, but then I'm going to also assume I2 is also 0 to put the circuit right on the edge of on the cusp of D2 turning on, and that is going to give me these conditions. So at that point, both I1 and I2 are 0, so KCL becomes I3 is equal to I4, and then I3 is equal to, now minus 4.3 minus 0.7 is the voltage right here, so that would be minus 5 minus 10 divided by R3, and then finally I2, sorry, I made a mistake here, this was, no, that's correct, and I4 is equal to 15 minus 4.3 divided by R4. So that gives you the condition for which the D2 is about to turn on. Now, if you change R3 and R4 in any way that the voltage V1 goes above minus 4.3, then D2 is going to turn on. And if you put set the condition so that V1 is anything less than minus V1 is less than minus 4.3, then only D3 is on. Hopefully this has been helpful in order to understand how the circuit functions based on the values of these resistors. Thank you for your attention.